Okay, so hi everyone, welcome to this lecture. So in this lecture, I want to work out on this problem. Okay, so I have taken this problem from the Zonda and Anderson book. Okay, so I find this question interesting, and also we learn a lot of concept in this. So it is not only about the rocket propulsion. Okay, in this you need a concept from the gas dynamics as well. So that is the reason I have taken this because our rocket propulsion and gas dynamic concepts have been used to solve this question. Okay, so my motto is to take this question is to make you understand about the rocket link between the rocket propulsion and gas dynamics. So gas dynamics equations are really important to understand your rocket propulsion, even your gas aircraft propulsion. Okay, that is the reason I have taken this question. Okay, and in the process we'll learn a lot of things to even about the isentropic relation, the critical condition. Sometime we also name it as a star properties in the cv nozzle. Okay, and about the isentropic process in the isentropic flow in the nozzle, then thrust calculation, mass flow rate calculation from different relation. Okay, so let's start solving these questions. So before that, I'll also suggest you to pause this lecture and try to solve this question by yourself. Okay, that will be even more better. Okay, so let's start solving this. Yeah. Okay. So the question is saying consider a rocket engine similar to that shown below. Okay. So this is how the actual rocket engine which will look like. Okay. So if you see the clear conversion diversion nozzle, you will not be seeing, but it is a conversion diversion nozzle. Okay. Liquid hydrogen and oxygen are burned in the combustion chamber. So inside the combustion chamber, they are burning the liquid hydrogen, liquid phase hydrogen as a fuel, and the oxygen, which is really required to oxidize your fuel, right? Inside the combustion chamber, producing a combustion gas pressure and temperature of 30 atm and 3500 Kelvin, respectively. The throat area of the nozzle is 0.4 meter square. So you see this area they're talking about, throat area. Okay, I'll draw the diagram as well. So they have already provided. The nozzle exit is designed in such a way so that the exit pressure exactly equals to the atmospheric pressure at a standard altitude of 20 kilometer, where the ambient pressure is they have given this much. So now you please, I hope you will appreciate why I have taken this question. So in the question, they are we need to understand we need to understand about the this statement this statement to be more precise. Okay, if you would have if you not understand this statement, then there is no point of solving this question further. Okay, because this is really required to understand to solve the question. Okay, so assume isentropic flow through the rocket nozzle with an uh, effective ratio of specific heat as a 1.22. So now we are no longer under the specific heat ratio value as a 1.4. No, now they have provided specific value. And why this gamma value got changed? Because now you are burning the hydrogen and oxygen, and due to the hydrogen oxygen combustion, your gamma value will be correspondingly they will be changing. Okay, similarly R will also change depending on the gas, or you're using air, or you're using methane, different gases you are having, right? So depending on that, gamma and R value will change. Okay, constant value of specific gas constant they have given. Now they are asking you to calculate the thrust of the rocket engine, thrust produced by this rocket engine, and to calculate the exit area of the nozzle, and that must be in meter square, and this thrust should be in kilonewton. Okay, and I'll also I'll also add this say that at this point that calculate mass flow rate by. Okay, that I'll discuss about this as well. Okay, in the further lectures. Okay, so this is the question. Okay, and this is the diagram, actual figure if you see, and this is what property inside the rocket nozzle. This is the geometry you are having. Okay, the question which already provided. Okay, so let me quickly draw the diagram, then we'll start solving this question. So if you see, let's say this is your inside we have this is kind of chamber, then you have a nozzle, you have this kind of nozzle. So this is, let's say you have a combustion chamber. So here after the combustion you are getting the high P naught value which is 30 atm, then high T naught value which is 3500 Kelvin. This is how, this is what they have already provided. So this is your combustion chamber. Okay, then at the throat area they have already provided. So throat area is your A star, which is 0.4 meter square. Okay, this is what they have provided. Now they are saying that your exit pressure. Okay, so let's say this is station number as a E. Okay, exit, and PE is exactly equals to the PA. That's what the question is saying, right? In the question we have the pressure equilibrium, the exit pressure exactly equals to the ambient atmospheric pressure, and the atmospheric pressure they already given this as a, so let me write this as a PA at a 20 kilometer altitude. Don't forget that this data what they have provided That means your rocket is operating at a 20-kilometer altitude. It is not at a sea level. So don't take this as a 1 bar or 1 atm. Okay, don't do this. Don't do this mistake. 5529 Newton per meter square, right? Now I'll tell you one cautious point for you. Here, if you see the stagnation chamber pressure, they have given this as a in ATM, and the exit atmospheric pressure they have provided in Newton per meter square. That means Pascal. So you need to very much careful while you will be using this equation in your formula. Okay, so that's the caution point for you. Then the one more thing, gamma don't use as a 1.4 and 287 don't use R value as a 287. Okay, don't do this mistake. So you should write this as a 1.22 and R value this as a 520 joules per Kelvin, joules per kg Kelvin. Okay, so this is what the flow situation is. Okay, now can you tell me definitely and what will be the what will be the exit Mach number? It will be subsonic or supersonic? Definitely it is going to be supersonic. Okay, so whatever value we will be getting, we should check that this should be this kind of a checkpoint. We should check whether we are getting supersonic value or not. If you are getting subsonic value, that means you are doing some calculation mistake. Okay, so this is okay. So I should start solving this question. So this is the flow situation, guys, and this is operating at a 20-kilometer altitude. Okay, fine. So the important thing is we should assume and not assume, they already given this statement that assume isentropic flow through the nozzle, rocket nozzle. So we should use this as in our solution simplification. Isentropic flow through the rocket nozzle, rocket engine nozzle. Anyway, okay. So the first thing is they're asking you to calculate the thrust produced by the rocket engine, right? Thrust produced in kilonewton. So now can you tell me which equation you will be using for the rocket for thrust calculation? So for thrust calculation, they already given that we have optimum expansion. That means we need not to worry about the pressure thrust. Pressure thrust is already now 0. So the equation which you will be using will be m dot p into Cj. So this is the equation to calculate for the thrust produced by this rocket engine. Okay. So the important thing is now the challenge which you are having is now calculating the Cj. Then another challenge is to calculate the mass flow rate of the propellant. Okay. So this is the challenge. So how you will calculate the Cj? So I'll be proceeding in a different way. Okay, not different way. You will generally find this method, but there is other possibility that you can calculate the Cj by different method. Okay, so don't restrict yourself by calculating. Yeah, this is the only way to calculate, but there can be other way as well. I'm not restricting you. You can use unless you can use different method unless until you should be getting the exact answer whatever we are getting. Okay, so I'll go with this method. Okay, so using isentropic relation and assuming that we have isentropic flow to the rocket nozzle, I can use P naught E by PE is equals to 1 plus gamma minus 1 by 2. So this is how your gas dynamics is important. Okay, gas dynamics is important to, otherwise you would have not used this relation, right? Okay, so the thing is I'll calculate the ME from here. Once I calculate the ME, once I'll get the ME, I'll use this this relation. Okay, using isentropic relation, I'll be getting the TE, and using TE, I'll be calculating speed of sound, and using Mach number, we will be calculating the exit velocity, that is Cj for us. Okay, so this is how I'll be proceeding, and this is how you should think of before proceeding for the solutions. Okay, okay, this is what the back calculations are, guys. Okay, so this is 30 atm. Don't mismatch with the unit. Okay, otherwise things will be okay. So the how you will convert this into the ATM. So the thing is you need to divide this by 101,325. Okay, you divide this, you will end up getting this as in a ATM. Okay, in a unit of ATM. So if you divide these, you will get this as 0.05456. Okay, and 1 plus everything will remain same. Okay, so substitute the gamma value as well. So don't forget that here we have a 1.22. So you simplify this, you will end up getting this as a 0.11 ME square, and send this power to this side. Okay, so when you take the power, this becomes 0.22 divided by 1.22. Solve is for ME, and let me do this quickly. And if you do simplify this value, you will get this as a 3.1199. Okay, you can also write this till 2 decimal places. You need not to go to till 3 or 4 decimal places. Okay, that is up to you. So you take this 1 to this side, that becomes negative. and you will get this as a 2.1199. So solve for ME under root of 19.2719, and ME, the exit Mach number, you will be getting this as a 4.38. So this is approximately the value which you will be getting. So this is how this is how you should proceed for the ME calculation. ME is your exit nozzle exit Mach number. Okay, nozzle exit plane Mach number. Okay, don't get confused. Now the velocity, we need to calculate the CJ, right? So for CJ, what I'll do, I'll use isentropic relation. Let me do it here. An isentropic relation is used for a particular station number. Don't move, don't go downstream or don't go upstream. You can use for a particular station number. That means I'll be applying the isentropic relation at the exit plane of the nozzle, and that can be done by in this way. T naught E by DE is equals to P naught E by PE raised to gamma minus 1 by gamma. This is the isentropic relation, right? If you're not if you have not taken this formula, please write this in a formula sheet. Okay, so PE is already known to you, P naught E is already known to you, P is already known to you, gamma is already known to you, TE is already known to you, T naught E, okay, which is 3500 Kelvin. So you can easily calculate TE from here, and so this ratio I got this as a 3.1199. Okay, and solve this. What you need to do, divide this by 3500. T, you solve for TE, you will get this as a 112.82 Kelvin. So this becomes your exit static temperature. So this value I am talking about, exit nozzle exit plane static temperature. Now I think it is easy now. So you can use ME is equals to CJ, or you can write this as a CE as well, unless until if you are understanding this, that is not the issue. So let me, yeah, so this can be written as AE. Okay, so CJ, and this becomes gamma R TE. T is known to you. R, you take this as a 520, I think. It should be 520. Yeah, 520. And R, you take this as a gamma, you take this as a 1.22. So you take this as a 1.22, and TE as a 112.82 Kelvin. Solve this, you should be getting this as a, so speed of sound, I got this as a, you take under root also, I got this as a 843.61 meter per second. So this is the speed of sound at the exit plane of the nozzle. Okay, corresponding you have a TE, right? So now what do, you know already ME from here. You solve for CJ, you multiply this to this side, and this will be simply AE, and solve this, you will get this as a 4. It was ME was 4.38, A is 843.61. Solve this, CJ will comes out to be 3695 meter per second. So this is the CJ value. That means at the exit of nozzle, you have this velocity, provided that you have optimum expansion in the nozzle. Okay, optimum expansion in the, that means PE is exactly equals to the PA. Okay, so my half of the job is done. We have done the hard work for the CJ. Now we need to do the hard work for calculating m dot P, mass flow rate of the propellant at the in the nozzle duct. Okay, so how you will now think of that, how you will calculate the m dot P. The m dot P, if you want to calculate, let's say at the exit of nozzle, so you need corresponding, let's say you want to calculate the exit of nozzle, so you need density at the exit, you need area at the exit, you need exit velocity. But the thing is, anyway you have a CJ, exit velocity we have, but we don't have the density at the exit, we don't have an area at the exit, and that's what the question is, that we need to calculate the nozzle exit area also. So that is the issue with calculating the mass flow rate at the exit plane of the nozzle. So what we can do is, so you cannot, as of now, you should not think of calculating the mass flow rate at the exit plane of the nozzle. You should think of, now the another thing is, we know the area at the throat, okay, throat of the nozzle, and provided that we have already the isentropic flow in the nozzle, so I can use this property, I can use this luxury to calculate the mass flow rate at the throat of nozzle. That means this becomes maximum mass flow rate. Okay, I hope you are understanding what I'm saying. So I'll proceed in this way. So the maximum mass flow rate, or mass flow rate at the throat, can be calculated using, so I'll directly write this as m dot P. So so one more important thing, you can also use this formula m dot p divided by a star under root of t naught divided by p naught r by gamma is equals to yeah 2 by gamma plus 1. You can use this one also, that is not the issue. You can also use this formula to calculate the mass flow rate uh, from the nozzle, provided that you have every data in this. T naught you have, P naught you have, A star you have, R you have, gamma you have, everything you have. This is anyway constant. This right hand side is. You can solve for m dot p. So what I'll do, I'll proceed in this manner first, using which equation? Rho star, sorry, A star. Then you have a velocity as a V star, critical velocity. So I'll proceed in this way. Then what I'll show you is using this formula, whatever mass flow rate we'll be getting, the exactly we should be getting using this formula, right? That's the physics, right? So what I'll do, I'll first calculate using this expression, then I'll use this expression to calculate the maximum mass flow rate. So I'll use the two different method, and we'll see whether we are getting the same value or not. Okay, so that I want to show you. So let me take this. Okay, so let me keep it here. Then we'll do the calculation. First, we'll do the calculation using this formula. Okay, so let's do the calculation for this as well. So the again challenging part is, you have anyway A star, you have already throat area, right? I don't have a V star, I don't have a rho star here. So for rho star even you need, so if you want to calculate rho star, there is a there is two method. Either you can go from rho naught by rho star using isentropic relation, and that is gamma plus 1 divided by 2 power 1 by gamma minus 1. So this is the one way. Or you can calculate by P star by RT star. But the thing is, if you want to go with this formula, you need P star, you need T star. Then you will be able to calculate the rho star, right? So what I'll do, I'll go with this method. Okay, so I'll be using isentropic relation. How I have got this formula, that let me tell you as well. Rho star by rho can be written as 1 plus gamma by 1 minus gamma by 2 Mach number square raised to the power this formula. If you please recall the gas dynamics isentropic lecture. So what you need to do now, you need to substitute Mach number as a 1 here. You'll end up why I'm substituting 1 here, because I want rho star, right? And for that you need Mach number as a critical Mach number. You want critical property, critical density, you need to substitute critical Mach number. What is critical Mach number? Because we are calculating rho star at the throat, right? Rho star at the throat. And what is the rho star? What is the Mach number at the throat? You always have a sonic Mach number, that is for sure. Blindedly you can say the Mach number at the throat for a supersonic Mach number at the exit, because my exit Mach number is supersonic, right? So your throat has to be choked always, right? So I can say m star will be 1. So I'll substitute as a m here 1, and the property which I will be getting will be rho star. You can do this substitution, m as a 1, you will end up getting this as a gamma plus 1 divided by 2 raised to the power this one. This is how you end up getting this formula. Okay, substitute everything in this. Okay, now the issue again is, you don't have a rho naught. You don't have a rho naught. How you will calculate rho naught? Using this formula. P naught equals to rho naught R T naught. You can write this. Then using rho naught, then using this P naught by R T naught, you can calculate rho naught from here. So I have done the calculation. So this is 30. This is in ATM. So you have to convert this into Pascal, because R and T is already in SI unit. So you cannot directly substitute ATM. And R is your 520 joules per kg Kelvin. T naught is, what is the value? 3500, right? I hope you're understanding the physics, why I'm going in this way, where I'm taking this formula. Okay, don't forget that we are doing the calculation for a throat location. So you solve this, you simplify this, you'll end up getting this as a, I got this as a 1.6701 kg per meter cube. Why kg per meter cube? Because in this expression every value was in SI unit, so you will be getting density will be also in SI unit. You can do the unit check here, you'll end up getting this as kg per meter cube only. Okay, fine. So yeah, the one thing is, now it is done, that you calculated the rho naught from here. Now you substitute rho naught here, and gamma you already know this value is constant value. You solve this, and okay, let me do this. Rho naught by rho star, you will get this as a 1.11 raised to the power 1 divided by 0.22. Okay, and solve this, you will get this as a, this value I got this as a 1.6069. Pardon me if I'm doing some calculation mistake. Is okay. So rho naught, yeah, from here you can calculate the rho star. So rho naught is 1.6701 and in the denominator 1.6069, right? So rho star you should be getting this. Please verify this value whether you are getting this or not. Yeah, we got the rho star as a 1.09392 kg per meter cube. Okay, you should be getting this value around. Okay, if you are getting 1.04, that is also fine. Okay, fine. So the rho star we have done the calculation. A star we already have. Now we need a V star. Now how you will calculate the V star? That is the question. So V star is nothing but the throat location velocity. And what is the throat location velocity? Your Mach number is already 1 at the throat. So this becomes V star by A star. So if it is 1, your Mach number is 1, then I hope you will be agree. V star will be equals to A star. So the thing is, we need to calculate the A star at the throat location. And for calculating the A star, we need a T star. How? Gamma R T star. Now we need a T star value again. So don't forget that we are doing at a throat location. Everything we are doing at a throat location. Every property is a star property. That is the reason I told you in the beginning of lecture that we will be going to learn about the star properties, throat properties, critical properties, right? So for T star, I hope you will be expert in the gas dynamics. Now we need to use this expression. Now T naught is already known to you. T naught is same everywhere in every location of every cross section of the nozzle location. So T naught is known to you. You can easily do the calculation for T star, and that value comes out to be 3153.15 Kelvin. So this is a T star value. You will please verify this whether you are getting this or not. So now you have done the calculation for T star. Substitute here R, you know, gamma, you know, everything you know. V star, or you write A star, one in the same thing, and you will be getting this as a 1415 approximately. You will be getting this as a 1.1415 meter per second. Okay, this is the value you should be getting. Please verify this value as well. Okay, all right, then what now? The thing is, everything is known to you. Rho star is known to you, V star is known to you, A star is known to you. You can simply do the calculation for m dot p, right? And why we are doing for calculation for m dot p? We need a thrust. In thrust expression we have m dot p, right? So substitute all the values in this. Rho star is 1.0, this value. A star is 0.4 meter square. Don't forget that this must be, area must be also in SI unit. V star will be 1415. To solve this, everything is SI in SI unit. M dot P, you will be getting this as a yeah, 587.91 kg per second. So you can write this approximately as a 588 kg per second. So I think now our hard work is over. We can simply do calculate for a thrust produced by this rocket engine at optimum condition, nozzle optimum condition. So that is nothing but m dot p into Cj. Now everything is known to you. Substitute everything, 588 multiplied by Cj. Now Cj is 3695. Now don't forget that they have told you to calculate the thrust in kilonewton. So we need to divide the complete value by 1000 or 10 to the power 3. So thrust will be, now you will be getting this as a, so I have got this as a this value, guys. So please verify this whether you are getting this or not. So you should be getting the value around this. Okay, so now we have done the calculation by that for a thrust produced by the rocket engine. Okay, that provided you have optimum expansion. So this is how you should proceed for the calculation. So I'm not restricting you. There can be another possibility for calculating the parameters. Okay, so I have given you the lengthy way so that you can understand the each and everything. Okay, the path you must be taking. Okay, the way to calculate the parameters, everything you should know. I have used a lot of equation in this, especially this one, P not equals to P equals to rho RT. You can write similarly. You can write in form of the stagnation properties. Okay. Now one more thing I want to show you that we can also do the calculation for a mass flow rate using which expression? This one. I want to show you this. And I'm very much sure that we will be getting same mass flow rate value. So let's do this calculation, and this will be maximum here. Okay, mass flow rate will be maximum because our throat is choked, right? We are getting the supersonic Mach number at the exit plane of the nozzle. So we will be having a maximum mass flow rate. not just mass flow rate. Okay, so I'll keep this as a m dot p max divided by a star is what, 0.4 meter square. Okay, then t naught is also in SI unit, and that is 3500. What is p naught? And this is 30 into 101,325 atm to pascal. We need to multiply with this value to convert into the pascal. And why pascal? Because every value must be in SI unit. Okay, and R value is 520, gamma is 1.22, and you solve this right hand side, which is constant, and I got this as a 0.5906. Okay, please cross check this value, verify whether you are getting this or not. You must be getting this. All right, so now you simplify this equation. You just need to do this. This value I got this as a 20.64. This value I got this as a 1.9462 into 10 to the power minus 5, and this is just m dot p divided by 0.4. You simplify this expression, and you will be getting this as a, you simplify this whole expression. Let's write over. Yeah, simplify this, you will be getting this as a m dot, let's write m dot max multiply by 1.0042 into 10 to the power minus 3. You take this into the denominator, and m dot p max will become this as a, yes, I got this as a 588.09 kg per second. So this is what I was trying to show you, that using both the expression, we will be getting the same result. So you can approximate this as a 588 kg per second. So you can see, using this expression we got this value, and using the basic mass flow rate equation we got exactly the same value. Okay, so this is what I want you to understand, that both the formulas are correct. The way of solving is, it depends on you, whether you want to use solve using this formula. But I'll suggest you that you please use this formula. This is easy, right? Things are given directly, and less chances of doing mistake. Because if you do slight mistake in this calculation, at the end you will be getting a wrong, let's say wrong row star. Let's say you got wrong row star. Everything will be then gone. All the hard work will be gone. The better you use this formula, there's a less calculation involved and less chances of doing the calculation mistake, right? Okay, then yeah, mass flow rate is over. The last part is calculate the nozzle exit area in meter square. So this is the reason I was saying that here we need the concept of gas dynamics. Okay, if you don't know this formula, then it is difficult to calculate the mass flow rate. And if you don't know the gas dynamics again, if you don't know the area velocity relation, okay, so now let's try to calculate the exit area of the nozzle. So what formula comes in your mind if they are asking you to calculate the exit area? So the area velocity, area Mach number relation will help you to calculate the exit area of the nozzle. How? Because every data is given in the area velocity, area Mach number relation. So let me write this. A y star is divided by equals to 1 by me. So now you will appreciate that why I was talking about the gas dynamics. Right? Now every data is given. So this equation is a function of just Mach number and the gamma. Gamma you already know, they have already provided. Exit Mach number, we already done the calculation. Everything we know, just we need to substitute the value. And that is the reason I was saying that gas dynamics becomes important here. You should be knowing the area Mach number relation for calculating the exit area. There can be another way to calculate this, but I feel this is the best way to, because every data is given in this. So exit Mach number is 4.38, and you solve this numerator, you should be getting this as a 3.1102, and the denominator you solve this, you will be getting this as a 1.11, and this value I got this as a 5.0454. And now simplify this. So you will be, so this value if you simplify, you will be getting this as a 180.10, and A by A star will become this as a 41.32 now. Now your A star you already know, which is 0.4 meter square. So you can solve this, and you can easily solve for AE, and that is 16.5 meter square. So please verify this value whether you are getting this or not. You must be getting the value around this. Okay, so this is how you should be proceeding for calculating the exit area. One more thing I want to emphasize that uh, in that they can also ask you for the calculate the nozzle exit diameter. Okay, they can also frame the question for calculating the exit sorry, nozzle exit diameter. So the only thing is you need to do is, once you know the exit area pi by 4 d, so you please use this formula because your nozzles are circular. Okay, so you need to calculate, then you can simply use this formula for calculating the diameter at the exit of nozzle. Yeah, they can frame this also. So I hope you have understood this numerical. You have learned so many things from this numerical. There was a lot of things. So if you are able to solve this kind of question, guys, you people will be easily able to solve the gate questions, because gate questions are just bits and pieces of this kind of lengthy numerical, additional this kind of conventional questions. Okay, so this was the additional question. Okay, they will be, if they will be asking this kind of question, they will be only asking just let's say for calculating the mass flow rate, they can ask just for calculating mass flow rate, or they can give the relative data, and they can ask for the exit diameter as well. So this kind of thing they can do, and probably if they will be playing with you, then they probably will play with the units. They can play with the units. Okay, so you should be knowing the, you should know the unit conversion as well. Okay, so I hope you understood many things in this question. Many doubts will be, now I am assuming that got cleared. Okay, if not, you can directly message me, you can ask me for your doubts. Okay, so let's meet in the next lecture, guys. Bye bye.